Good morning, everyone. My name is Dion Molt, and for 15 years, I've been working with open source and doing software development. I'm also trained as an architect, and I worked in architecture for a number of years. And 2 years ago, I joined Lend-Lease and have started to look in more detail at OpenBIM across all disciplines. So today's presentation is going to be a very fast-paced introduction to OpenBIM and open source, and we're also going to do a short technical workshop and deep dive into the IFC specification and how you can build your own digital tools. So there will be two halves of this presentation. And in the first half, we're going to start with some really high-level concepts, like the definition of OpenBIM, the definition of open source, and we're going to show some cool things that we've created with it, kind of like a show and tell. Then we'll get more concrete and we'll move on into what native IFC looks like. We'll see how IFC describes our built environment, what's inside an IFC file, and how to read the international specification. We'll then go over some of the relationships that you can express with IFC and touch on some of the lesser known ones. In the second half, we'll translate this high-level discussion into actual code and software. You'll see how to read and write IFC data in Python yourself. You'll also use the Blender BIM add-on to debug and analyze your IFC data. We'll see how it can be used through a graphical interface as well as through code. Traditional BIM authoring tools like Revit and ArchiCAD don't use open data standards. So the data that Revit uses to describe walls is different from ArchiCAD and so on. And this means that we can't transfer walls very easily from one software to another. But more importantly, it means that the quality of our data just does not exist. There are so many ways to describe something as fundamental as a wall, never mind more complex things, and we're too busy fighting over whose wall description is the best instead of focusing on more important things. What this means is that the BIM that we're all doing nowadays is not much better than storing our data in a spreadsheet, because everybody has a different way of doing it. And in fact, it's worse than spreadsheets. Because at least with a spreadsheet, everyone can access it. It doesn't expire, we don't need subscriptions, and we can control how it is structured. Right now, the vendors dictate these terms, not our industry. The good news is that we can solve this technically using open data standards. And the better news is that we can solve it culturally, because our industry is starting to realize that unstructured, traditional BIM data is a problem, and the solutions are out there. So OpenBIM is basically applying open data standards to BIM. OpenBIM is a set of international standards on how to digitally describe our built environment. And if everybody agrees to speak the same language, then we can easily create processes that work seamlessly across disciplines and across software. This digital language is created by mutual agreement in our industry, not vendors. And I just want to pause and stress this point. OpenBIM is the closest our industry has gotten to agreeing with each other through counseling. The most difficult aspect of standards aren't the technical difficulties, it's the political and social difficulties for us to agree to work with one another. It's too easy to fall back to traditional BIM data. But OpenBIM has come further than any other open data specification in creating mutual agreement. The most popular OpenBIM standard you've already heard of is IFC, which has the purpose to describe designs within our built environment. But it's not the only one. We have BCF for issue management, IDS for model checking, BSDD for data translation, and other efforts by other organizations. So whereas OpenBIM is fundamentally about the freedom of our data, open source is the flip side of the coin. It's fundamentally about the freedom of users of the data, or your own freedom. And this is why we call it free software. It's got nothing to do with price. It's to do with 4 very specific freedoms with our digital tools. The 4 freedoms are the freedom to use our tools for any purpose, to learn how our tools are built, to modify our tools to suit our needs, and to share our tools with others so we can all work together easier, and when we make improvements, we can share the improvements with everybody else. So when we combine open source and OpenBIM, we regain the freedom of our tools and our data. In the future, the majority of our workforce will know how to code. And this means that the majority of our workforce will expect to have freedom with our data. The software industry has already made this change. All the technology around us already relies on open source and open data standards. It's almost impossible for new software to be built without this. the computer graphics industry is also starting to follow suit. Our AEC industry is far behind and we need to do better. The fundamental problem is that we've normalized our way of thinking in terms of vendors. We need to start thinking in terms of data, where we have the freedom to build a tailored data pipeline, which is optimized for our projects. And ultimately, this tailored data pipeline will be optimized for the digital built environment that we all want. So today we're going to focus on IFC, and here's the textbook definition stolen from their website, but basically it's the ISO standard for the digital language that describes our built environment. And this goes from design to construction and operations. The scenario we're most familiar with is that IFC can share 3D models kind of like this, but it's quite superficial, because the way most of us produce IFC data is by exporting and importing from these traditional BIM applications. Whenever we press that export button, we know that half the model data and intelligence is lost. And the output is usually not much better than a 3D format with some metadata tags. You could probably do the same thing with an OBJ file and a CSV. You don't really know where the data is kept, how it is kept, whether it translates correctly or not, and so superficially produced IFCs, or translated IFCs, from traditional BIM turns into a read-only snapshot, which nobody can really trust. So today, I want to go further than traditional BIM and further than translated OpenBIM. I want to talk about Native IFC. This is where we can author BIM models directly in IFC with no imports, no exports, no data loss, no data translation, no model linking, and we can still author it using multiple tools. And we can create our own tools to author it too. All the demonstrations I will show you today are created with pure native IFC, no translations, using only free software. So here's an image of my living room back in 2019. And this image is quite special because it's not a photograph. It's actually a render of an IFC model. Every object you see is a BIM object classified into IFC object types with enough metadata to be scheduled, with detail down to every individual blade of grass. This might be considered over-modeling with traditionally closed BIM tools, but it's actually quite average if you use computer graphics software to create your BIM models. This render is also special because it's not an artistic render. It's a photometrically correct, a validated light simulation using material data stored in the IFC itself. There were no test renders, no lighting adjustments, no color pickers used, just pure, rich data with numerical physical measurements from product samples combined with the free software Radiance. Radiance is the gold standard for lighting simulation. So the image you see on the left is the simulation adjusted for the CIE average human eye, and the right is a photograph. So just with pure native IFC, your BIM model can store all the data you need to produce a lighting simulation just like this. So here's some derived work by somebody online who then took my light simulation and extended it. He did thousands of simulations to cover every frame taken from a head-tracked VR environment and calculates the daylight glare probability and vertical illumination for lighting engineers. This is a luminance simulation with the false color values on the right. Native IFC can also support point clouds. So here we're taking some measurements off a construction site, but interestingly enough, semantically, it's not just a whole bunch of points. The points themselves can be assigned to BIM objects, so they're intelligent geometry. So if you're looking at as-built verification, heritage, or model archival, your IFC data and point cloud scans can actually integrate. You can also generate drawings from IFC. This is a Revit sample model taken out into IFC, and then we fully annotated it and documented it in the IFC itself. No Revit, no AutoCAD, just pure native IFC, which creates all the grids, all the dimensions, labels, and so on. Most software in our industry creates 2D drawings using proprietary formats, like DWG. Other derived formats like DXF or DWG itself and PDF also miss out on all of this rich BIM data. In contrast, these drawings are generated into the open SVG format. And this means that anybody can open it on a standard web browser. You don't need special software. You can use it on a tablet, your phone, or anything with no restrictions, unlike DWG. SVG also supports semantic metadata, so we can store IFC data within the SVG itself. So if I have a 2D rectangle on this plan, it actually knows it comes from a 3D object. It knows it has material properties and tags. And just by generating a single plan, because it has all this layered rich data inside of it, a viewer can interactively display different properties with different hatches, symbols, and labels all on the fly. There's no need to spend hours shuffling around tags on a sheet because your viewer starts to be able to dynamically generate them. And being native IFC, this means that our drawings, not just our models, but our drawings themselves, the diagrams, become programmatically queryable. So in the same way that you can write scripts to query and analyze your model, you can write scripts for your 2D drawings even after they've been published. So imagine if on site on a tablet, you could click through markers and labels on fully interactive drawings, which can go back and forth between 3D models and 2D drawings and auto-generated specifications, attach BIM documents, tables, using completely free viewers that worked in a regular browser on any device. This could be the future of drawings and diagrams if we switched away from proprietary DWGs and moved towards open data standards. Native IFC also supports structural analysis. It supports all the information you need to create analytical models with boundary conditions, load cases, combinations, and structural members. It can be linked to any structural engine you wish. And once the simulation is performed, all the results and reaction forces can then be stored back in the native IFC. So in these images, the structural analysis was done using an open source software known as CAAD. But there are other tools which can also be used. Another tool is AdaPi, and this lets you use high-level code to describe structural IFC components. And just like before, you can then simulate this in CAAD, or you can use a different simulation package, such as Calculix, which is also open source. Native IFC also works at the concept stage. And it's also possible to develop custom tools and custom workflows, like in this example, where you can sketch out and trace walls, which are automatically generated to real BIM walls based off wall types on the fly. This system started out as a user prototype and now works as a wall creation tool. Here's another example at concept stage of a scene drawn in VR. This is an example scene taken from Blender, which we then translated into native IFC. And although the scene has things which look like rough sketches, it can be annotated and scheduled, and it gives you enough freedom to think in non-manifold geometry. So here's the same scene, we bring it into Revit through IFC. We can also generate geometry within IFC. So here's an example where we start with a series of non-manifold spaces, and you can perform some topological analysis to determine space connectivity and things like that. And you can generate entire buildings and cities. Again, we're working directly with native IFC. So everything you see here, all the resultant spaces know their spatial functions. All the walls, doors, and windows are all stored in the native IFC data. You can then pass all of this through an evolutionary solver and start scoring spaces with respect to arbitrary values. In this case, the software known as Homemaker scores these spaces based off architect guidelines in the book A Pattern Language. And the software we're showing here combines 3 free software. We have Topologic, Homemaker, and the Blender BIM add-on. Topologic provides topological analysis of the geometry to determine what spaces are connected to one another. Homemaker uses Topologic to generate these designs in native IFC, and the Blender BIM add-on helps visualize and modify these native IFCs. Then there are buildings designed completely open source, like the WikiHouse and the Wikilab projects, and open source ecology. So just imagine if your design process was like Wikipedia, where anyone could edit your BIM model. Here's a recent residential project by the Opening Design Studio, and you can see all their 3D detailing in native IFC and their workflow using free software like Git for their versioning and CDE. Native IFC also supports costing, completely integrated into the model with formulas and derived quantities. So there's no need to export models, link them, and map models. You just directly create your cost schedules within your model alongside your design team. Even more complex operations like automatic formwork calculations can be performed and recorded directly in your cost schedules. Program scheduling can also be done within native IFC in a fully integrated manner. No exports, no linking. You can create calendars, work schedules, task dependencies, calculate critical paths, floats, early and start dates, and record actual versus scheduled. Naturally, we can also visualize progress or generate animations. So all these animations were generated directly from the IFC, and as you update the model or the schedule, the animations automatically update alongside it. There's also automated model checking, project asset libraries, classification system integration, design constraints, ownership, liability tracking, but I don't really have pretty pictures for these, so we'll just skip over it. So how does Native IFC achieve all of this? IFC describes a series of concepts that have meaning in our industry. Each one of these concepts is known as a class, which is how the industry foundation classes got its name. So for those who know programming, this is very much like classes in programming. And for those who don't worry about it. Each class has a definition provided as part of the international standard. These classes have attributes to give information about them, simple things like name or description. And some of these attributes refer to other classes. And this allows classes to be connected using relationships. Some of these classes are semantically meaningful to humans, and others are a bit more like raw data that only makes sense when you combine it with a semantic class. And when you put all of this together, the semantic and the unsemantic classes and the relationships, this is known as the IFC object model. And this is how we can query and generate native BIM data. Any software can create and describe BIM concepts using IFC classes using any programming language. If you want to transfer or store some of these classes, you can serialize it into one of these formats. The one most of us know is the IFC file. This is a plain text step-based serialization, but there are others like XML, JSON, or binary. Or you might not use a file at all, and you might use a relational database or structures purely in memory, or access it through an API and exchange little snippets of JSON and XML. And in total, there are nearly 1,000 IFC classes, and we won't have time to go through all of them today. But what I can do is provide a high-level overview and pick out some classes as an example of what's possible. And because there's so many classes, the definitions of these classes are categorized in various ways. One of these is a hierarchical tree. And this hierarchical tree allows similar classes to be grouped together. And when you group them together, this means that any classes lower down in the tree inherit the attributes of the parent classes. And this is quite a great way of understanding classes, generally for computers. And you can think of this tree as a dictionary of IFC classes. And there's a big list on the Building Smart online documentation website. This dictionary is written in a computer language known as Express. And a definition of a class using this Express language under the hood kind of looks like this. And it's really scary, and most of the time you wouldn't need to look into it unless you're a software developer. But what this means is that because the dictionary definitions are all written in a computer language, it guarantees that our digital tools can all speak it consistently. And this huge hierarchical tree is really good for computers to understand because it represents when all the attributes and relationships are inherited. But sometimes it's not so great for humans. And for humans, there's an alternative way to categorize these IFC classes. An alternative categorization method is to use these 4 main groups. Within these groups, they then have subcategories of more classes within them. And these categories are designed for different types of audiences to understand. So at the bottom, we have classes that are catered for really technical people because they are the fundamental building blocks, like classes that represent geometry. And at the top, we have categories which are most relevant to very specific disciplines, like HVAC classes or electrical classes or structural classes. And in between, we have classes that are shared across multiple disciplines. And some people prefer to browse this dictionary of classes using this method, and others prefer the alphabetical list, and some prefer the hierarchical list. And all of these appeal to different people, and that's okay. They're just different ways to navigate through the IFC concepts. But just navigating through this dictionary is not enough, because a dictionary only tells you the meaning of words or these concepts, but it doesn't tell you how to construct sentences. And if we want to describe scenarios in our built environment, we need to combine classes in a mutually agreed manner. To understand how to put these classes together meaningfully, there are a series of fundamental concepts described in the Building Smart docs. This is the chapter to read if you want to find out more, and today I will focus on 3 simple concepts to give you a taste of what's possible. The first concept is the IFC project class. The reason this is the most fundamental concept is because whenever you describe a BIM project, you must use this IFC project class. This is how you define your project. And once you've defined it, other classes may then be related to your project, either directly or indirectly. So your project becomes the entry point for software and users to start looking for more information. You can view the documentation for IFC project by browsing here. You'll find some translations for the class, a changelog of modifications, the ISO definition, and its categorization in the dictionary tree, but most importantly, you'll find its attributes. And if you click on attribute inheritance, you'll find that an IFC project has 9 attributes, denoted by the first column. You can also see the name, the data type, and the description of each attribute. The cardinality column tells you if it's optional or if it can contain more than one value. And because the IFC project concept is so fundamental, you will find it in every single IFC file that you have, or almost. And because IFC files are plain text, you can just open it using a text editor, and you'll find something that looks a bit like this. Every line represents data from a single IFC class. Each line starts with an identifier, the name of the class, followed by a comma-separated list of all the attributes. And if you search for IFC project, you'll find a line that looks like this. And in this case, the identifier is 11. The class name is IFC project, and here are our 9 attributes shown in order. The name of our project is 123foo, and it has an object type of residential. And to read these attributes, the string values are single quoted, numbers, integers, and decimals are not. You have null values represented by a $sign, and references to other classes use a hash prefix. And enumerations are pre- and postfixed with a period. So as an example, the IFC project has its units in context attribute referencing another IFC class just below it. This then represents another class which defines an SI unit stating that the linear dimensions in our project are recorded in millimeters. So if you spend half an hour before bedtime reading 10 lines of IFC every day, it'll kind of make sense within a week. And if STEP looks scary to you, here's the same thing in JSON format. You can see it's a bit more readable, but at the same time, it's a bit larger, but it's the exact same data, just stored in a different way. Another concept is spatial decomposition. Spatial decomposition is how IFC describes how larger spaces break down into smaller spaces. And you can use this concept on any class that derives or inherits from IFC spatial element. So if you remember the dictionary tree of IFC classes where classes inherit attributes and relationships from parent classes, in the dictionary, IFC spatial element has many subclasses. So this concept can be applied to all of these subclasses. So let's say I've described an IFC site and an IFC building. The spatial decomposition concept allows me to create a relationship using a third class known as IFC rel aggregates to link them together. The way I link them together is because the IFC rel aggregates class has 6 attributes. 2 of these attributes can refer to other classes, and specifically, the relating object attribute refers to larger things, and the related objects attributes refers to smaller things. So if I reference my site and building accordingly, I have essentially described in Native IFC that my building is situated on this site. I can repeat this pattern again and again and again to create a tree of spaces and stories and wings of buildings and sites and roads and traffic lanes and so on. So here's another simple fundamental concept to describe material associations. If we want to describe that a slab is made out of concrete, we just use an IFC slab class and an IFC material class, and we connect them using a third IFC rel associates material class. And just like the IFC rel aggregates class that we use for spatial decomposition, you'll notice that classes that contain the word rel can be used to relate things together. So here, the IFC rel associates material class has, again, two special attributes which you can use to connect our object with a material. And there are a lot more concepts which we can't cover in detail, but we'll skim over a few just to get an idea of what's possible. So here's a simple concept which describes how a work schedule can contain tasks. And this has applications both in construction sequencing as well as facility management. In construction scheduling, a work schedule is a collection of tasks that must be completed over a specific time frame in order to reach the final deliverable for the project, such as constructing and commissioning a building. We can then extend this concept with this one, where tasks can be linked to objects in our BIM model. And in this concept, our task is set as a construction task, which effectively means that our task results in a wall being constructed. Tasks can also have sequential relationships. And in this scenario, a predecessor task, such as setting up formwork, has a finish to start relationship to a successor task, such as pouring concrete, with a lag time of one elapsed day between them. If you don't know these terms, that's okay. They should make sense to people in the construction sequencing profession. These concepts are quite straightforward, but some concepts are very difficult to understand. To show you one extreme, there are concepts which describe details about implicit and parametric geometry, such as for rail alignment curves, which require a detailed understanding of computational geometry to appreciate. Other concepts are a bit broader and more intertwined, mixing disciplines such as those for costing, scheduling, resource management, productivity rates, and performance histories. Here's a really complex diagram showing the interdependencies between 4D, 5D, resource management, and productivity. But the good news is that the majority of concepts that you'll deal with are very straightforward, and the difficult ones, like this, have already been resolved by software developers. Now, there are over 100 concepts described in IFC. I've only explained 3 basic ones and skimmed through a few more, but there are so many I won't have time to go through today. But I hope you can see that IFCs can be incredibly data-rich, apply cross disciplines, and offer more than what we're currently doing to digitally describe our built environment. It's an absolutely incredible industry effort to standardize and localize the amount of interdependent data that we work with. Right now, our industry is a bit like the early days of the internet, where websites mostly worked with certain browsers and not others, and the shared protocols and languages of the internet were still being formed. Closed data, vendor-specific APIs, lossy data translations through imports and exports is not the future. The future is when our foundations all natively speak the same digital language formed through mutual industry agreement. It took a long time for the internet to get to where it is today, and that's from the most digitally savvy industry out there, which is the IT sector. In contrast, our AEC industry is divided and diverse, and slowly catching up to the norm in other digital systems. We need to work together to improve this. And a common myth I hear about IFC is that it's like a PDF for BIM data. And this is only partially true, because most of us use IFC like a PDF file, and proprietary vendors like to treat it like a PDF, but this is changing. Because thanks to free software, any user can now move away from this traditional and translated BIM and start taking advantage of the full breadth of capabilities of Native IFC. And these capabilities are not new. They have been specified in the international standard since the early 2000s, but only now is software catching up to it. So yes, you can treat it like a PDF, but it's designed to be so much more. So in theory, you could ditch Revit today, and you could write all your BIM using Notepad. And writing your BIM models with just Notepad is an excellent way to learn OpenBIM for those of you who are up to the task. In fact, that's how I learned how IFC worked. So if you're up to the challenge, I highly recommend bringing out Notepad and just writing raw IFC with text and see what happens. But for today's talk, we're not going to do that. And instead, we're going to look at how to write code using some free software. And the good news is that the most advanced software for working with Native IFC is all free, and it works on all platforms, so everyone can try it out. The software we're going to demonstrate today is the Blender BIM add-on. And the library we'll use is the IFC OpenShell library with the Python programming language. And if you don't know Python, don't worry, because Python is just English with a bit less punctuation. The BlenderBIM add-on started around 2019. We had designed a small building in Blender, and it came to the point that we needed to start documenting and assigning BIM data. So we had two choices. We could either rebuild the model, which was fairly detailed and it had some complex junctions and geometry in a tool like Autodesk Revit, or we could build all the BIM functionality we needed back into Blender. So we wrote an experimental script on option number 2, and we figured that it took about 83 lines of code to export Blender geometry to IFC. And that was really exciting for us because this was an internal project. We didn't have any client deadlines, so that 83 lines of code kept on growing. A month and a half later, we packaged the scripts as a download for the public. And soon after we packaged the scripts, even before we finished our building, somebody online discovered it and repurposed it to generate BIM models to visualize compactor machine data that was used to build a highway. Now, obviously visualizing compactor machine data is not top of your list of features when you're developing a BIM app from scratch, but it goes to show that with a digitally savvy industry that we're trending towards, there are these positive spillover effects from the development of free software that you simply can't predict. Anyway, we continued developing it over the next year or so. We delivered our commercial building, and we built a suite of utilities that were separate from the BlenderBIM add-on, but could be used in an integrated fashion. And we'll talk a bit more about these utilities later in the talk, but essentially we created a framework for a Swiss Army knife of BIM tools that could be combined and mixed and used both within and outside Blender and across other applications. But the easiest way to get started with this exciting world of free software is to download Blender. And if your computer doesn't give you admin rights to install software, then just download a zip file and extract it. Then download the BlenderBIM add-on and install it. And apart from a BIM tool for users, it also bundles all the software development libraries in a single download, so you can get up and running in one go as a developer as well. Blender comes with Python pre-installed, so you don't need to install Python on your computer, and it comes with an interactive Python interpreter and a way to run full Python scripts. Now, if you want, you don't need to use this. You can install everything separately and install Python on its own. But if you use Blender and the BlenderBIM add-on, it can get you up and running in under 5 minutes. So let's activate the built-in Python interpreter in Blender and run some Python code. And if you don't know what you're typing, just press Tab, and that will trigger the autocomplete function. And if you don't know any Python, the basics are on the right-hand side of the slide. So the module in Python that provides all the functions to interact with IFC is known as IFC OpenShell. So to use it, type in import IFC OpenShell, you press enter, and now when you type in IFC OpenShell and press the period key and press Tab, the autocomplete will trigger and it will show you all of the IFC OpenShell functions which you can use. The function we're going to use is called open, which opens an IFC file, and it will give you back an IFC object which you can store. And if you press Tab on the variable which you just created, you can see all the functions we can perform on our IFC file. So let's say this is the IFC file that we just opened. So again, every IFC class is on a new line with an ID number at the beginning. Again, like before, the IFC project class has an ID of 11. So if we want to retrieve data about our IFC project, let's use the byId function of IFC OpenShell. And this will give you back a project object. So if we type out project and autocomplete on it, you can find all the attributes. And if you type the name of an attribute and press enter, you can view the attribute. So here's the full script just to get the project name. It's 4 lines of code. Now, I've experienced that about half of the BIM models that I come across actually get their project names wrong or inconsistent. So with 4 lines of code, you can start to automate a project name check. And if you wanted more data than just a name, you can use the getInfo function. Now, having to know the ID of the IFC project class is a bit inconvenient because it keeps on changing on every single file. Now, instead, you might know the global ID. And so you could do that using the biannual function. And if you also didn't know the global ID and you want to generically search for any IFC project in any IFC data, here's a really simple example to search by IFC class. And in this example, we'll search for all IFC wall type classes. And this lets us find out how many wall construction types are defined in our project. So let's print out all the names of our wall construction types. Now, unfortunately, again, almost every single BIM project that I've come across has incorrectly recorded the names of their construction types. So let's fix it. And you'll see that this is all it takes to improve the quality of your BIM data. And once you've done editing, just save your IFC file back out. Now, there's so much more functionality in Python that we can't cover today. But for the programmers in the audience, here's a really simple example of how to create a native IFC from scratch. We'll start with a blank file, and we'll create our project class. Now, we'll define our project units. And then we'll create a building, and we'll spatially insert our building inside our project. Then we'll create a slab, a roof, and 4 walls. And let's put all our building elements inside our building. And there we go. Here's a minimal BIM model in just 15 lines of code. There's a crash course online that you can search, which will go in more detail. Now, again, for the programmers in the audience, the reason we could build a BIM model so quickly is because IFC OpenShell offers a high-level API to manipulate OpenBIM. And this API is unique in the industry. It's the only tool that comprehensively offers native IFC manipulation via code across 40 different modules that do everything from geometry to 4D and 5D and structural analysis and more. And all of the API calls are high level. So all the little details like purging subgraphs, handling IFC version differences, ownership history tracking, date time conversions, and all of that, really nitty-gritty stuff are all automatically resolved for you. The IFC OpenShell system is also unique in the industry that it supports transactions, so you can undo and redo operations. So here's that minimal 15-line BIM file that we created, opened in the Blender BIM add-on. And you can see our project, the building and the elements inside of it. Now, our 3D scene is empty because we haven't created any geometry, but the data attributes came through correctly. So at this point, we can start to augment it using a visual interface. So we can select our building and add things like internationally standardized metadata about a lease agreement. And we can use other tools like the IFC CSV tool, and we can export a spreadsheet schedule of our walls. And if we want to, we can edit the spreadsheet and then re-import it back into the IFC file. And this lets us very quickly audit and edit IFC data in bulk. So you can see that we can mix code-generated BIM models, visual interfaces, as well as spreadsheet interfaces, all in native IFC and interoperate. Here's another example. If your IFC files are really large, we can use the debug panel to start isolating high polygon objects. And you'll notice many artifacts kind of like this coming from BIM models where the IFC file size can multiply by 10 times with no added value. We can produce a list of objects and fix them in your original BIM application. Or if your IFC file is coming in the wrong location, you can quickly use the IFC patch tool to shift and rotate coordinates to fix it. This is a very common task when dealing with incorrectly geolocated IFC files. There's so many other tools in the Blender BIM add-on to interrogate your IFC data. Within the Blender interface, you can author and graphically audit architectural, structural, 4D, 5D, FM data. You can create new IFC projects or edit existing IFCs from other software. This is completely new to the industry. No other industry tool goes to the level of depth of the Blender BIM add-on in its ability to do native IFC authoring across all of these disciplines. The IFC patch tool gives you the ability to fix common errors often seen in translated IFCs, like georeferencing issues, or even upgrade and downgrade IFC schema versions. Many of these patching functionality is also unique in the industry, like upgrades and downgrades of partial IFC data. The IFC diff tool lets you compare changes between IFCs, including not just the geometric and metadata changes, but changes in relationships and non-architectural data as well. This is also unique in the industry, because other model comparison software will only focus on surface-level data, like geometry or simple metadata changes, not deep indirect data relationships. The IFC CSV tool lets you export IFC data and edit it in a spreadsheet format and perform bulk edits and bulk class changes to clean up your IFC and then re-import that data back to IFC. The BIM tester tool lets you automatically audit model requirements, including support for micro-MVDs and the information delivery specification, or the IDS standard. And for those interested, we've published an academic paper on how this new approach allows us to describe complex BIM requirements in human terms that make sense to project managers in multiple languages and still are machine readable and can be automatically checked all for free. Then we have IFC COBie, which does audits and translates COBie information for facility management. And an interesting fact about COBie is that it's specified in IFC, but this is almost never correctly delivered by proprietary applications. And for people who want to do COBie correctly, the IFC COBie tool is one of two known tools which can actually do it in the industry. IFC Clash performs clash detection across and within multiple IFC datasets. And we've also got experimental code for IFC Sferjak, and this is like a visual node programming for IFC. So for those of you who know Grasshopper or Dynamo, Sferjak is the equivalent for Blender. In fact, Sferjak is the Russian word for cricket, which I'm probably pronouncing incorrectly. And there are also tools for conversions to other systems like SVG drawings, 4D imports from Primavera and Microsoft Project, GIS conversion from CityJSON, conversion to CodeAster for structural, geometry conversions to OBJ, Collada, GLTF, or GLB, STEP, IGES, and XML. And all of these free tools are available in multiple ways. You can access it through a graphical interface, or you can use it from a command line on any operating system, or use it through code as a library. And this toolkit gives you the freedom to mix and match as you see fit and tailor it for your situation. So if you're a power user, check out the Blender BIM add-on. And if you know code, check out IFC OpenShell. As an example, last year we built a custom pipeline which combined these tools in various ways to audit, process, and generate data tailored to a large commercial project. So these tools aren't just something that you get packaged in a particular way. You can mix and match them as you see fit. And in this pipeline, certain IFCs had drawings automatically generated, export errors from proprietary vendors were automatically patched whenever there was a new upload. We used Git to track version changes, and COBie data was automatically extracted. Clashes were automatically checked, BIM exchange requirements were audited based on the execution plans and contracts, and various spreadsheets of particular data were extracted as well. And this is an example of the flexibility that these open utilities gives you. You can use these utilities as complementary to your existing workflows. I also want to stress that right from the beginning, the development priority for the Blender BIM add-on have been driven from solving immediate user problems. It has never been the objective to complete a checklist of features or to compete with a specific proprietary software. And this is why the current feature set of the Blender BIM add-on partially overlaps the capabilities of many proprietary software packages, and in other cases, it actually has features not found in any other software. Users have always been and always will be at the heart of free software development because the developers are users themselves. And if you are a user and you have a problem, you let us know and we can help you determine how the technology evolves. If you're also a programmer, you can add the code yourself. And most of these tools are actually quite new. They were only written in the past couple of years by the community. The Blender BIM add-on itself is still in alpha testing. So by the time many others see this talk, these tools will have changed, have improved, new features would have been added, but you can be part of this journey and shape how these tools evolve. I'm also really happy to share that these tools were recognized and won the Building Smart 2020 Technology Award submitted by Lendlease and Cox Architecture. The project has also been awarded an EPIC Mega Grant and sponsorship by the Google Summer of Code project. And these projects, although free, are actually used under the hood in many other offerings, both commercial and free in the PropTech ecosystem. And we believe that investment in free software helps promote the diversity and competition in our industry's tech offerings. It's also being introduced to academia and taught in a few universities across Europe. Researchers and students are also now contributing to build features for really bleeding-edge BIM capabilities, like lighting support in Native IFC and upcoming BSDD, BCEF API specifications. There are now 99 people who have contributed to the codebase and growing. And the things we're doing with Native IFC is uncharted territory. But it's a territory that we need to start exploring together. So today, I've only shown a tiny portion of what's possible with Native IFC. As I've mentioned before, there are nearly 1,000 IFC classes and more than 100 IFC concepts that can be described. I've shown you how to get started with Python and IFC OpenShell and the BlenderBIM add-on. But there's so much more than just the BlenderBIM add-on, and I'd like to introduce you to this wider world of free software. One great example is Ladybug Tools, which does environmental simulation. Ladybug Tools has changed our industry. It has brought environmental simulation to the masses. Because simulation engines are really complex, but the user education done by Ladybug Tools and the packaging that they provided through the visual nodes have allowed architects across the world to create a better built environment and better buildings all for free. Now, it doesn't use IFC, but it does have its own open data structure, known as the Honeybee JSON structure. And because of its open nature, we can integrate Ladybug Tools into Blender. And this is really exciting, because it's the first time Ladybug Tools is paired with a really strong mesh modeling package, which mesh modeling is kind of a common weakness in proprietary BIM software. Ladybug Tools also integrates into FreeCAD, which is another huge topic, because FreeCAD has a huge ecosystem of modules. They call these workbenches. And this goes from the BIM and architectural world to robot simulations, mechanical modeling, CAM, CNC controls to CFD, finite element analysis, and land and infrastructure works. It's a really, really broad scope, all in one completely free package. And there are cloud or web-based packages, like IFC.js and ZeoKit, which lets you build web applications with IFC. And Open Project, which is a completely free open CDE platform, which has seen a huge amount of development over the past year. We have vSense, which can visualize live sensor data, or Speckle, which acts as interoperability tools between many platforms, or Compass, which performs robot simulation. The list of free software available to us just keeps on growing. There's OpenStreetMaps, QGIS, Cloud Compare, Radiance, and so much more. Now, today, I'd like to invite you to join the open source architecture community. The open source architecture community are people working together to build free, integrated, standards-based tools for our industry. And this is the first large-scale initiative of its kind to bring a community together to work across the ecosystem of free software, instead of focusing on single pieces of software. And there are over 1,000 members representing both big and small firms across all disciplines like architectural, structural, MEP, landscape, FM, cost, scheduling, and so much more. And if you'd like to learn, you can find community members online there, building new free tools every single day, learning from one another, and really happy to help. And the OSArch community has launched a series of initiatives. We help to provide news coverage for free software in the AEC industry, which you can subscribe to here. We also provide a wiki, which helps document hundreds of free software. There are guides on how to start learning this software, as well as tutorials on basic scripting, a human-friendly introduction to OpenBIM, IFC, BCF, and COBie, and how to get better open data results from proprietary software and so on. We also have a forum where users and developers across many free software projects share their work and look for ways to integrate across disciplines, across applications, and share code. And this sharing has resulted in a lot of cross-pollination and synergies across software applications that otherwise would never have integrated. There's also a catalog of video tutorials for all sorts of topics to get started with free software, and we host monthly meetups on a show and tell basis for various software projects. You can also join our live chat room, where there are about 50 users and developers online across different software every single day, and you can watch live as they develop new features, fix bugs, and answer questions. This is an incredibly exciting time for our industry, because for the first time, we as users and professionals have the freedom to move away from traditional siloed BIM and build a new native standardized digital pipeline together for our built environment. This pipeline is across disciplines, across platforms, across countries, and as we move away from a vendor-centric approach to a native open data approach. This will empower you to decide how our AEC tech should be like. And for those in the audience from larger firms, now is the time to invest in standards and free software. Imagine how different our industry would be if we did this investment 10 years ago. But large or small, whether or not you can code, everyone can make a difference. We need power users who can test, report bugs, write documentation, create tutorials, suggest new features, improve usability, translate to other languages, deliver presentations. And by working together, we can build a new digital built environment that we have full control over. Because sooner or later, our AEC industry will catch up, and we will expect this digital freedom. So please, drop by the open source architecture community, and let's change the industry together. Thank you very much, and I hope you enjoyed my talk.